Hello and welcome. My name's Neil Lakritz. I'm a research engineer for Bose Corporation, and I'm here to talk about sound. The goal is to give everyone some basic information about what sound is and how it works. For example, consider a live performance. You're in the audience, the musicians are playing, the sound travels to your ears, and you hear Mozart. But how does the sound get from the instruments to your ears? And what are your ears actually sensing? In this series, we're going to take a look at what sound is and how it gets from there to here. And along the way, we're going to get some basic definitions of a few audio terms. Now, I'm an engineer, and sometimes I'll start talking about watts this, amps that, hertz those, and someone will speak up and say, "Neil, stop. What are you talking about? What do these words mean?" And that's really a fair question. What is a watt or a hertz? And I've realized that to understand a lot of technology, you really just need to know a set of terms and definitions. They're not magical, they're just definitions. For example, I can show you right now exactly what a hertz is. Here's a hertz. Heinrich Hertz, to be exact. He was a famous German physicist, and after he died in 1894, they named a unit of measurement after him, the hertz. We'll get to know this term as we go along, but first, let me tell you what else we're going to talk about in this series. In section 1, we're going to go through the physics of how sound gets from my mouth to your ear, or from musician to audience. In the second section, we'll look at the anatomy of a sound wave. We'll introduce this weird, unnatural sounding thing called a tone, and we'll discover that all real-life sounds are actually made up of lots and lots of tones. In section 3, we'll find out how sound waves interact with objects, big objects like walls and small ones like your head. And we'll learn how spaces affect sound. So if you're ready, let's get started. In this section, we're going to talk about the physics of how sound travels. And of course, no discussion of physics would be complete without tennis balls. If we're going to talk about how sound works, the first thing we need to understand is this thing called air. Look around you. Do you see all the air? That's what makes it so hard to talk about air. It's invisible. So to help visualize this, I'm going to take my hands and clasp them together. Do you see the air that's tucked in there? Imagine that's a little sack of air in my hands. Now, I want you to think of this tennis ball as that sack of air. The next thing I want you to do is to realize that the room is filled with these sacks of air, floor to ceiling, wall to wall, front to back, full of tennis balls. You can't see across the room because there's tennis balls everywhere. If you have that picture in your mind, we're basically done. Everything else we're going to discuss follows from this picture. So let's start by investigating our little sack of air. What do you notice? Well, for one thing, if you push on it, it pushes back. If you try to squeeze it, it wants to come back to its original shape. Likewise, if I take a balloon, which is full of air, and I squeeze it, or I stretch it, and I let go of it, it always comes back to its original shape. Fundamentally, this illustrates that air has some spring to it. And that's really the main thing you need to know about air right now. It's got spring. Now, how does the sound get from my mouth to your ears? As I'm talking to you right now, how do you hear me? Am I just sending out sack after sack of air towards you? Is that what you're hearing? All these little sacks of air going by your ears? And when you answer, are you sending me back a sack of air? I have to tell you that when I started studying acoustics, that's exactly what I thought. But remember, the room is full of tennis balls right now. It's a sea of tennis balls between you and me. I don't have a free path from my mouth to your ears. I can't even see you because of all the tennis balls in the way. Well, here's a way to visualize this. Imagine that my mouth is over on the left-hand side of this tube and your ear is over here on the right. So when I'm talking, what I'm really doing is I'm pushing a tennis ball on the left side, and that's causing a ball on the right side to move a little bit. It's not the case that a tennis ball goes all the way from one end to the other. In fact, let's do the experiment. If I push on the tennis ball here on the left-hand side, what's going to happen over on the right? Well, 3, 2, 1, push. It moves, right? And that's the way sound works. You push the first ball, which pushes the second ball, and so on down the chain. Air doesn't actually go from one end to the other, only the push travels down the tube. Now, how long does it take for a push on the left to show up as motion on the right? Is it instantaneous? Let's take a look at these 3 balls. When I push the first ball, it gets squished and it starts to move over. As it moves over, it starts to squish the second ball and starts it moving. Then the first ball gets tired of being squished, so it starts to expand and slow down. Meanwhile, the second ball has moved over a little bit, squishing the third ball and putting that ball into motion. Then the second ball starts to expand and slow down. Now the third ball has moved over, and so on. This process of squishing, moving, and expanding continues down the chain. Squish, move, expand is how sound travels. Now, there's a slight delay between when I push on the left side and when the right ball moves. It takes some time for the sacs of air to go squish, move, expand, squish, move, expand, squish, move, expand. It's called the speed of sound.
The speed of sound is roughly 1,100 feet per second or 350 meters per second. To put this in perspective, consider a group of sprinters. The starter pistol is fired. In 1 second, how far do the sprinters get? In that same second, the sound of the starter's pistol has traveled 1,100 feet, about the length of 4 football fields. Like sound, light also travels as a wave, but light travels much more quickly than sound. During a thunderstorm, this difference in speed can be quite noticeable. If the storm is very close, you see the lightning and hear the thunder at approximately the same time. But if the storm is off in the distance, you might notice a delay. The light reaches you almost instantly, but the sound travels more slowly. A delay of 5 seconds means that the storm is about 1 mile away.
Now think about how the sound of the thunder got from that spot 1 mile away to you. Well, remember the tennis balls? Squish, move, expand? All of those little sacs of air between you and the storm got squished, moved, and expanded one after the other until the sound finally reached your ears 5 seconds later. So that's it for this first section. We've talked about how sound travels, and we've talked about the speed of sound. At this point, you might be saying to yourself, okay, I know how sound travels through the air, I know how fast it goes, but what is it? What is sound? And that's what we're going to talk about in the next section, the anatomy of a sound wave. When you hear a sound, what are you actually sensing? It turns out that your ear is sensitive to vibrations. And just to prove that to yourself, put your fingers on your neck and hum to yourself. What do you feel? You feel a little vibration, right? That's how sound is made. Your lungs are forcing air up through your larynx. Then your larynx shakes the air to create the vibrations. Finally, it comes out of your mouth, and you can shape your mouth to make things like words. And it's those vibrations that get sent into the air. Looking back at our sacs of air, you can see what happens. If I vibrate this first sac of air, That vibrates the next sac of air, and so on down the chain until I'm finally vibrating the air by your ear. So you actually hear vibrations. Now, we need a way to talk about vibrations. So here's a simple example of something vibrating. Up here I have a spring, and down here I have a weight. And you'll notice that the weight is going up and down. Now you might ask the question, how fast is it vibrating? How many vibrations per second, or cycles per second, is the weight going through? In other words, how many times each second does it travel from up here to down here and back again? More specifically, we're asking, what is its frequency? I'm going to time the vibrations, and when I get to 10 seconds, I'll stop. All you need to do is count the cycles. We'll start when it's up here, and when it gets back up to the top, that'll be one cycle. All right, here we go. Stop. How many cycles did we get? 10. Okay, 10 cycles in 10 seconds, so that's one cycle per second. Now, a cycle per second gets another name. It's called a hertz. So since this weight is vibrating at one cycle per second, we could say it has a frequency of 1 hertz. So that's how we talk about vibrations. Remember, vibrations are what we hear. So this weight is vibrating at 1 hertz. What does it sound like? Well, nothing. It's vibrating too slowly to produce a sound wave you can hear. In general, the range of human hearing is about 20 hertz to 20,000 hertz. Since the prefix kilo means 1,000, we can say either 20,000 hertz or 20 kilohertz. Below 20 hertz, we might still feel the vibration, but we can't really hear it. And as the frequency gets up to around 15 or 20 kilohertz, your ear has a harder and harder time hearing that vibration until you can't hear it at all. Now, sound travels through the air as a wave, the same way a water wave travels through the ocean, or a vibration travels along a length of rope. If we start vibrating this rope at one end, the vibration actually travels down the length of the rope as a wave. Notice that the rope itself doesn't move from left to right as the wave travels from one end to the other. This is similar to the way sound travels through the air. The air itself moves only slightly as the wave passes, but the sound wave can travel for miles. Here's a sound wave in action. On the left, we are going to start vibrating a volume of air. This air vibrates the next volume of air, and the next, and the next, and so on down the chain. This diagram shows what happens to the air as the sound wave passes. At the bottom, we can see the pockets of air squishing, moving, and expanding. The waveform on top shows how the air is being affected. It's being squeezed and expanded, and here it's at its normal, relaxed state. This is slowed down so you can see it clearly, but the rate at which the wave goes across the screen is actually the speed of sound. This shows you what the vibration looks like, but what does it sound like? This sound is called a tone, and the shape that represents it is called a sine wave. If you're a musician, you might recognize that this tone corresponds to the note A above middle C. The actual vibration is 440 hertz, so at full speed, this wave would be vibrating 440 times per second. Now, we'll increase the frequency of the tone. The wave is now moving up and down 6 times faster than before. It still moves across the screen at the same rate, the speed of sound. However, the shape has changed. Now listen to the difference. It has a higher pitch. By increasing the frequency of the tone, we've raised its pitch. So frequency is just another way to describe the concept of pitch. I'm going to give you another demonstration of frequency and pitch. What you're looking at here is a visual representation of what you're hearing. For example, what you are listening to right now is a 100 hertz tone. Well, 100 times a second, that's pretty fast. But vibrating back and forth quickly is what devices like speakers do very well. So the speaker in there is moving back and forth 100 times per second. Well, what do you notice about the pitch of this particular note? It's pretty low, right? Now listen and watch for what happens as I change the frequency. Here's 200 hertz, 300, 400, 500 hertz. Now what do you notice as I go up in frequency? The pitch changes, right? Do you notice how the shape is changing too? Well, let's keep going. This is 600, 700, 800, 900, 1,000 hertz, or 1 kilohertz. Let's keep going. 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz. Now, let me make an adjustment so you can see this better. All right, again, 5 kilohertz, 6 kilohertz, 7 kilohertz, 8, 9, 10. So frequency is pitch. Frequency, measured in hertz, corresponds to pitch. Slow, low-frequency sound waves produce low-pitch sounds. Really fast, high-frequency waves produce very high pitches. Now, we've talked about frequency, but there are two more important parts to every sound wave: wavelength and amplitude.
This is an animated diagram of a sound wave. The distance between here and here is the distance between a repetition. Notice that this distance is the same as this distance or this distance. No matter where we measure from, there is a constant distance between repetitions. That distance is called the wavelength. What happens if we raise the frequency? The wavelength gets shorter. Remember, the wave itself travels at a constant speed, the speed of sound. So as it starts vibrating at a faster rate, its wavelength gets shorter. And lowering the frequency causes the wavelength to get longer. There is a direct relationship between a sound wave's frequency and its wavelength.
So frequency and wavelength are used in different situations to understand different things about sound, but both terms basically describe the same thing. Low-frequency sound waves have long wavelengths, and high-frequency sounds have short wavelengths. All right, we've talked about frequency and wavelength. Now there's one more part of a sound wave we need to talk about. As I turn this knob, what do you see in here? As the height of the tone changes, the volume changes. The height of the tone is called the amplitude, and amplitude is just another word for volume. A small amplitude is a quiet sound, and a large amplitude is a loud sound. So when someone walks up to you at a cocktail party and says, "Hi, I'm a tone," there are two questions you want to ask to really get to know them. First, you'd ask, "What's your frequency?" And they'd say, "I'm 500 hertz." You might respond with something witty like, "Nice to meet you, 500 hertz." "And what's your amplitude?" And they say, "I'm this loud." Given these two bits of information, frequency and amplitude, you know everything about that tone. Of course, you could have also asked, "What's your wavelength?" But that's essentially the same question as, "What's your frequency?" All right, So we now know the basic elements of a tone, but how does this relate to the sounds we actually hear in real life? In the next section, we'll put all these pieces together and show how we can use tones to cook up some real-life sounds. We've spent some time listening to tones, but how do these tones relate to anything we hear in real life? Well, if I play one note on this piano, you hear it, right? And if I play a second note, you hear that as well. And if I play a third note, you hear that. Well, what happens if I play 3 notes simultaneously? What do you hear? It's called a chord. So I can take multiple notes, add them together, and get a chord, which is much more interesting. It turns out that just as a chord is made up of individual notes, each note is made up of individual tones. That's why we care about tones, even though in real life we rarely hear them. Tones are the fundamental building blocks of sound. And as we said before, each tone has a frequency and an amplitude. Now let's pull all these concepts together. We're going to play 3 sounds for you: a piano, a flute, and a tone. Listen and see if you can tell which is which. Sound 1. Sound 2. And sound 3. Now what can you tell me about the sounds we just heard? How are they the same and how are they different? Let's listen again. The tone, the flute, and the piano. They're all the same pitch, specifically A above middle C, which happens to be 440 hertz. But there's something very different about these 3 sounds.
Here are 3 graphs of 3 different sounds: a simple tone, a flute, and a piano. The top graph is the tone. It represents a vibration of 440 cycles per second for 2 full seconds. Next is the flute. It is also vibrating at 440 hertz, but notice that the height of the wave varies and the loudness of the flute varies as it plays. When the flute is quiet, the amplitude on the graph is smaller. When the flute is louder, the amplitude is larger. The bottom graph represents the piano. Like the flute, it also has amplitude variations that correspond to changes in volume. These graphs show 2 seconds of vibrations at 440 hertz, or 880 complete vibrations from start to finish. This is useful for looking at the overall shape of the sound, but we can't see much detail. If we zoom in for a closer look, we can see each individual vibration. The top graph is the tone. It has a very simple sine wave shape. The flute waveform underneath it is much more complex. However, there is a similarity between the sine wave and the flute. They both have the same fundamental frequency. Both are vibrating at the same rate, which is why we hear them as the same pitch. The more complex shapes on the flute waveform are what make it sound like a flute instead of a tone. Now, let's examine the piano. Again, notice that the repetition rate is the same as the other 2 instruments. So, the piano played the same note as the other 2 instruments, but like the flute, the piano is more complex than the tone. This additional complexity helps you distinguish the sound of a piano from a flute from a tone. Remarkably, a French mathematician named Fourier was able to prove that these more complex shapes we see with the flute and piano are actually nothing more than additional tones being added to the 440 hertz tone.
Now we're going to look at these waveforms in a slightly different way. In order to explain this, I'm going to tell you about a hobby of mine, which is baking. I love making cheesecakes. I inherited from my grandmother the world's best cheesecake recipe. To make this cheesecake, I need to know which ingredients to put in and how much of each. All that information is in the recipe. Making real-life sounds, like a musical note for example, is very similar to baking. I just need to tell you the recipe. But baking a sound wave is quite easy because there's only one type of ingredient, tones. All I need to do is tell you the frequency and amplitude of every tone in the sound. And I can capture this recipe information in a type of a graph called a frequency response diagram.
In these diagrams, the horizontal axis shows frequency and the vertical axis tells you the amplitude. The higher the amplitude, the louder the tone. Notice that all three sounds have a spike at 440 Hertz. This lowest tone is the fundamental frequency. Since the fundamental frequency is the same for all three sounds, we hear them as the same pitch. Now, look at the flute and the piano. They both have additional tones above the fundamental. These higher frequency tones are called the harmonics of the note. It's the particular pattern of harmonics that makes the flute sound different from the piano, even though they're both playing the same note. The fundamental frequency determines the pitch, and the harmonics give the note its individual character.
So, every sound we hear can be broken down into individual tones, and each tone can be described in terms of its frequency, or how fast it's vibrating, and its amplitude, or how loud it is. But what happens to these sounds in the real world, say in a concert hall or a living room? In the next section, we'll talk about some of the things that can affect sound as they travel through the air. And in particular, we'll look at how spaces affect sound. Up till now, we've talked mostly about the frequency and amplitude of a tone. Now, we're going to change gears slightly and start discussing wavelength.
In general, the way a wave interacts with an object depends on which is bigger, the object or the wavelength. This applies to both sound waves and water waves. As these ripples encounter a small twig, not much happens. The length of each wave is bigger than the thickness of the twig, so the ripples pass by relatively undisturbed. As the wave travels along, it encounters a large anchored dock. Since the wavelength is much smaller than the dock, it reflects. The wave bounces off of the dock. Whether the wave reflects or not depends on how the wavelength relates to the size of the object.
The main thing to remember here is that when you're talking about how a wave interacts with an object, the size matters. And this is true whether you're talking about water waves or sound waves. Let's do an experiment to demonstrate how this works with sound. I'll start by playing a very high frequency tone at about 12 kilohertz. A 12 kilohertz tone has a wavelength of about 1 inch or 3 centimeters. Now when I walk in front of this speaker, listen to what happens. I blocked the sound, right? Since my body was much larger than a wavelength, I did a pretty good job of blocking the sound wave from reaching your ears. Now, I'm going to lower the frequency to 120 hertz. At 120 hertz, the wavelength is approximately 9 feet or 3 meters. Again, listen to what happens when I walk in front of the speaker. No difference, right? Since the wavelength is much larger than my body, the sound wave basically ignores my presence. I'm going to repeat that experiment with a slight variation. Again, I'll play a 12 kilohertz tone. Now, listen as I spin the speaker around. Listen for a difference. Do you hear a difference? It's quieter when it's pointed away. The sound wants to go out in all directions, but since it has such a short wavelengths, it gets blocked by the device. That's why high-frequency sounds tend to be very directional, like light from a flashlight beam. Let's try that again with a 120 Hz tone. Again, what do you hear when I point the speaker away from you? There's almost no difference. Low-frequency sound is very different from high-frequency sound. Low-frequency sound, as it leaves a source like this, goes out in all directions. Since the wavelength is so much larger than the source itself, the sound doesn't get blocked. It goes out in all directions, just like ripples in a pond. Now, we're going to do an experiment with the sound here in this room. So we need to switch from the microphone that's here on my collar to this one here in the room. Now, you can hear what the room sounds like. I'm going to say a tongue twister, and I want you to listen and see if there's any difference when I'm facing towards you versus when I'm facing away from you. In particular, listen for the high frequency sounds, like S's, S, and sh. Here we go. She sells seashells by the seashore. She sells seashells by the seashore. Now, listen to what happens when we go outside. She sells seashells by the seashore. She sells seashells by the seashore. When we're outside, it sounds very different when I'm facing away. That's because you're hearing mostly the lower frequency tones of my voice. The higher frequency tones have such short wavelengths that my head actually blocks them. And without those higher frequencies, my voice sounds quieter and slightly muffled. Let's try that experiment again. She sells seashells by the seashore. She sells seashells by the seashore. Here indoors, the situation is slightly different because you have walls. In here, it doesn't sound all that different whether I'm facing toward you or away from you. Even though my head is still blocking those high-frequency tones with their short wavelengths, those sounds are going to bounce off the walls and eventually get to your ear, whether I'm facing you or not. In general, the way sound gets to you is through a very indirect path. Some sound goes directly from the source to your ear, but the majority of the sound bounces off a few walls, ceilings, floors, tables, chairs, before finally making it to your ears. Sound that travels directly from the source to your ear is called direct sound. When sound bounces off surfaces before it gets to you, we call it reflected sound. So, what percentage of sound comes to you directly? Well, in a typical concert hall, assuming you sit back from the orchestra by at least 20 or 30 feet, about 90% of the sound is reflected and only 10% is direct. What this means is that the room has a huge impact on the sound you hear. Okay, let's run a few more experiments that will help to demonstrate some of the weird behavior of reflected sound. Now, for these experiments to work, I'm going to need you to get up and move around your room, so headphones won't work for this. And make sure you are at least 5 or 10 feet away from your TV or speaker. First, I'll play a 2 kilohertz tone. This tone has a wavelength of about 7 inches, or 17 centimeters. Now do this with me. Close off one ear like this. Now, when I play the tone, move your head back and forth and up and down very slowly, and listen for how the sound changes as you move. What do you hear? Well, the volume changes, right? In some spots, the volume is quite loud, and in others, you can barely hear the tone at all. Okay, let's do another experiment. I'm going to connect this microphone to this display over here. See, it's picking up the sound of my voice. Now, for this to work, you need to keep your head still. See what happens as I move the mic? Notice that in some places, it picks up a lot of sound, but in other places, it barely gets anything. That was what was happening when you moved your head around. So, what's going on? Before we answer that, let's run one more variation of the experiment. This time, close off one ear again and keep your head very still. I'll vary the frequency of the tone upwards, starting from 2 kilohertz at a constant amplitude. Again, listen for how the sound changes. What do you hear? As the frequency changes, the volume varies. So in all 3 experiments, the volume changed. What's causing this?
In most rooms, the majority of the sound that reaches your ear is reflected sound. When a sound wave hits a reflective surface, like a wall, it bounces back. When it does, the reflected wave combines with the original wave. What your ear actually hears is the combination of these 2 waves. At this spot, the amplitude variation is large, so if you stood here, you would hear a loud tone. But if you stood here, you would hear a small amplitude or quiet tone. This point is also called a null. The distance between these points is 1/4 wavelength. In the case of a 2 kilohertz tone, that's about 2 inches. And as the frequency changes, the location of the null moves.
Of course, that was an idealized computer model, but it gives you an idea of what happens in a real room. And it explains why, as you moved your head around, the volume of the tone changed. The point you need to come away with is that the location of these nulls is controlled both by the location of the wall and the frequency of the sound. And every room in the world displays this type of behavior, even this concert hall. Regardless of where you sit, and regardless of the room, the sound that gets to your ear is highly dependent on the shape of the room. Some frequencies will reach your ears with high amplitudes and some with low amplitudes. The room affects the sound. By now, you should have a better understanding of how the music gets from the instruments to your ears and what happens to the sound along the way. The topics we've been discussing here are a good foundation for a deeper understanding of acoustics. And these basic concepts will help you in your further explorations of how sound works. When you hear a sound, it's really pretty amazing to think about all the different things that are happening as the sound travels to your ear. Of course, it's also nice to just sit back and enjoy the music.